Okay, here we go. So thank you everybody for joining our wiki seminar series. Today actually is the last day of our seminar series for this academic year. So thank you very much, Professor Aron Meltzner, who from Nanyang Technological University in Singapore, who is closing all this year of activities in our seminar. So a little bit about Professor Meltzer. He was trained as a field geologist, and his research bridges earthquake and climate science. Earthquakes and sea level rise both individually impact communities in catastrophic ways, but tectonic processes and sea level change operate on timescales of decades to millennia, in many cases longer than instrumental or even historical record. His interests lie in using geology to extend the modern instrumental record back in time in order to study past changes in sea level and solid earth deformation due to tectonic and isostatic processes. A longer record of these past changes gives us better context in which to understand the processes operating at present and hence to forecast future changes and events. He earned his PhD from Caltech, California Institute of Technology in 2010, and have been at Nanyang Technological University in Singapore ever since. First as a postdoc and now as a faculty. He is currently a Singapore National Research Foundation Fellow and Nanyang Assistant Professor in the ASEAN School of the Environment at NTU. And a PI at the Earth Observatory of Singapore. So with this word, we're very honored to host you, Aron. And today he is going to talk about unprecedented insights into subduction zone behavior from coral, microatoll, paleogeodetic records. So thank you very much, and the podium is yours.
All right. Thank you very much, Nicholas. So, and thank you for the invitation. And it's my pleasure to be talking to you. So I'm going to be talking for the next 30 minutes or so about coral microatolls. And coral microatolls, we basically give us information on past relative sea level. And I'm going to be focusing my talk today on how we then use that to understand tectonics, earthquake histories, and paleoseismology. But these corals can be applied just as well to studying past sea level changes. So I think my understanding is that there's a breadth of background, of your background. So some of you may be familiar with this, others this may be entirely new. Please don't hesitate to interrupt me and ask any questions. I'm gonna try to explain what I'm doing, but feel free to interrupt me. So what we have pictured here is a coral microatoll. It's a fossil coral microatoll, which simply means it's dead. It died a while ago. And what makes it, two things that make it a microatoll. One, it's a coral. It was at some point in the past growing as a coral. And these concentric rings that you see on top are really the hallmark of coral microatolls. And so I will explain to you how they grow, how they form, why they have these concentric rings, and what these concentric rings tell us. Before I get into that, though, just some background, just to make sure we're all on the same page here. So relative sea level. That's a term that simply refers to the difference between the land and sea height at a given location. And it's affected by changes in either land or sea height or both. And just to kind of illustrate what I mean, if I'm standing at the beach and I'm looking out at the water, and all of a sudden I see a coral reef come out of the water and emerge and be exposed to the air, I cannot know, without some independent information, I cannot know whether it was the land that rose, bringing the corals out of the water, or whether the sea level dropped. And that's an important limitation of what we're able to observe, because when we're using the geological record to go back in the past and we use corals or anything to reconstruct changes in relative sea level, we cannot know whether, just from a single observation at a single location, whether the change was in land level or sea surface height or a combination of both. All we can see
And
is
what time is it right now?
Well, it has that town.
is there a question?
No, go ahead. Go ahead.
Okay, sorry. So all we can know is the net change of sea surface height and land level. And there are a number of processes. Many of them are shown here, that can affect either sea surface height or land height or both. I anticipate that many of you are familiar with this, so I won't go into this in detail, but suffice to say, I'm going to be focusing today on changes due to tectonics. But as you will see, I'm going to be touching upon some other changes because really all of these processes are inseparable when we're making observations. And at the very end, in my last slide, I'll talk a little bit about how what I'm going to be spending most of my talk on can be generalized to study relative sea level changes anywhere. So coral microatolls, as I've said, provide records of past sea level. And if we were to imagine a cross-section a vertical cross-section through this coral, we might see something like what's pictured here. And corals, or at least the species of corals that we're interested in, are annually banded. They have, during one part of the year, they grow more densely, and another part of the year less densely. So they have annual growth bands, not completely different from tree rings. And that's useful for us because when we look at a cross-section, we can actually count these annual growth bands, and they are a very precise clock that shows that gives us information about the elapsed time as the coral grew. And the coral will start growing well below low tide, well below whatever controls its highest level of survival, its upper level of growth. And every year it will accrete one new annual band to its skeleton. And so we can imagine that each white line here represents 1 year of growth. So, you count it, we have 5 years of growth here. So I've indicated this is year 5. And the green line here is the outer perimeter, which is the living part of the coral. The interior part of the coral dies as it grows outward. Again, similar to tree rings. So at any instant in time, this outer green ring is the part that's alive. And here we're still at 5 years, well below, I'm just going to call it simply sea level here, but really it's the lowest water levels of the year, or really what controls the highest level of survival. So let's fast forward in time now, a few more years. And we're now up to year 11. So not too much has happened, except that the coral has grown higher and bigger, and it's closer to what I'm calling sea level. But in fact, as I suspect some of you know, many of you know, sea level is not uniform over time, and even the lowest water levels of the year are not the same from one year to another. There are many different processes that might cause sea level or the lowest tide of the year to be lower one year from another. And I will go into some of that later in this talk. But for right now, let's just simulate that at the next instant in time, something happens causing sea level to drop by several centimeters lower than it had been in any time in the previous few years. And what that's going to do is cause the uppermost few centimeters of this coral to be exposed for a sufficient length of time that the uppermost part of the coral dies. And so you can see, I'm going to go back and forward again, you can see that the uppermost few centimeters here, and by the way, just for a scale, we can think of these growth bands as being about 1 centimeter of growth per year. That's a typical amount of growth for Porites corals. And so here the uppermost few centimeters turned from green to white, signifying that they died. But below what we call the highest level of survival, the outer perimeter remained green and the coral remained alive. Now let's fast forward a few more months and let's assume that sea level got higher again. And so the coral was able to grow upward and outward from below the highest level of survival. And so what I've simulated here is another 3 years of growth. And so now let's another snapshot, another sea level lowering will cause the uppermost few centimeters to die once again. And as we repeat this process, the coral will once again grow up and out from below that highest level of survival. Now, this is a cross-section on the left. If you imagine this cross-section now in 3D or in map view, each of these bumps here, each of these ridges in cross-section is a concentric ring in map view. And that's how these concentric rings form. Now, there are these short-term sea level fluctuations that I just talked about, but over the long term, if sea level is stable, if there's no net sea level change over timescales of decades or longer, then we would expect the center of the coral, the elevation of the center of the coral, to be similar to the elevation of subsequent rings. If there's net sea level rise over the lifetime of this coral, the outer rings should be higher than the center. And if there's net sea level fall, the outer rings should be lower than the center. And so we see, so the corals are recording this combination of this high frequency sea level fluctuation signal superimposed on any longer term trends that are decadal to centennial to even millennial. And so this is what the coral records, and this is what we look for in these corals to give us information about sea level changes in the past. And importantly, when we see a coral like this with concentric rings, we know that the coral was growing up as high as it could possibly grow throughout its lifetime. And so we can then use differences in elevation from one ring to the next to tell us about sea level changes over the lifetime of that coral. And we can even compare corals that grew decades or centuries or millennia ago with corals living today to reconstruct sea level change from that past point in time to modern day. And just to show you a living coral, microatoll, you can see that the center, you can see these concentric rings in the center, and these concentric rings, the outer concentric ring on 2 of these corals here are alive, and you can see that from the bright pigmentation of the corals. But the portion of the corals that are dead are no longer able to clean themselves. They're no longer able to remove sediment that accumulates on the surface. And so you see this very sharp distinction between sediment-covered, mud-covered interior concentric rings where the coral is dead, and this brightly colored outer concentric ring where the coral is still alive. Just one more example. Again, we see mud-covered center and brightly pigmented outer perimeters to these corals. And what we also see in both of these photos is that for any one concentric ring, it's at a uniform elevation. And even when you go from one coral to another, the outer perimeters and the inner rings, when the inner ring, any particular ring on an individual coral is at a uniform elevation. And when you compare one coral to its neighbor, those are also at the same, the corresponding rings are also at the same elevation. And so that tells us really that these rings, the die downs and the growth are really limited by water level. And this contrasts to other causes of coral mortality where either an entire coral might die or the mortality might be patchy and not at a uniform elevation. If we see patches of dead coral that are not at a uniform elevation, we will not necessarily assume that the death was related to sea level. But where we see these corals with these really nice uniform elevations, that is a compelling piece of evidence that the mortality was related to sea level, and we can use that to reconstruct past sea level. So this is now, what I'm showing now is a coral from Sumatra. And this was a coral that was a coral microatoll that was happily growing on the 25th of December, 2004. But in the Boxing Day earthquake on 26th of December, 2004, this coral was uplifted about 1.25 meters and brought up out of the water, and the entire coral was killed. But you can see that it was at a uniform elevation. Its top is at a uniform elevation. And we took a slab through this coral with a chainsaw, and I'll show you in a moment the procedure we go through for extracting a slab and extracting information from that slab. But both from the side view and the top down, you can see that we extracted a slab, but just because of limitations of the chainsaw, the chainsaw didn't reach all the way through the coral, but we extracted a critical part of it. And I'll show you what we saw once we extracted it, but first let me show you the process of extracting the coral. So here we have a chainsaw, and we're cutting a slab. This is not the same coral. This is the coral that I showed you in the opening slide. Let's see if this video plays. All right, so that's using a hydraulic chainsaw to cut through the coral. Once we cut through the coral, we extract a radial slab that might be 12 to 15 centimeters thick. Often it will break into a number of pieces, so we fit the pieces back together. We apply an epoxy so that they remain together. We'll drill a horizontal, we'll mark, so we'll actually survey some points on the top of the coral, and then we'll project down from those surveyed points to mark a horizontal line on the coral. And that is how we know exactly how this slab was positioned when it was originally in the field. We will drill holes along that line so that when we then take a slice through the interior of this slab, we still have that information about the original horizontality. And we'll also drill some samples for radiometric dating. And we'll typically use a combination of uranium thorium and radiocarbon dating. There are some advantages and pitfalls to each technique, and so I won't go into that in today's talk. I'll answer some questions if you have any, but we usually use both methods just to check for replicability. Ideally, the radiocarbon and uranium thorium dates will agree with one another. Once we've done all of that, we'll place the slabs in concrete so that they stand up vertically, and then we bring them to a marble factory, and we'll do what I call bread slicing them. We'll take these 12 to 15 centimeter thick slabs and slice them down into bread slices into about typically 13 or 14 millimeter thick slices, which are the ideal thickness for X-raying. So I've got another video here to show this process of bread slicing the coral. And so then with that, we end up with a number of slices that are, as I said, 13 or 14 millimeters thick. We'll pick the best slices that have that best preserve the information, and we will X-ray those slices. And 13 to 14 millimeters is the optimal thickness because that's thin enough that the X-rays will penetrate through the slice, and we'll have a clear image of the annual banding, the annual growth banding, which combines the denser growth in one part of the year and the less dense growth in another part of the year. But if we slice the coral too thin, it becomes very brittle, very fragile, and it might break into 100 pieces, and then before we have a chance to X-ray it. So 13 to 14 millimeters is about the optimal thickness where it doesn't break up too much, but we can get a sharp image in the X-ray. And so here you can see the process of X-raying the coral. And so once again, this is the coral that from Sumatra that was uplifted about 1¼ meters in 2004 that we took an X-ray of, and I'll show you now that we took a slab of, and I'll show you now the X-ray. And so just to make sure you understand what you're looking at here, in the lower right is a top-down view of one radius of the coral. As I said, the chainsaw wasn't big enough to get through the entire coral, but we were able to get the critical information. And so the coral would have started growing somewhere down below this image, and it grew radially upwards and outwards from where it started. And you can see the annual growth bands. So each light and dark pair is 1 year of growth. And so this coral was growing radially upwards and outwards until some point in time. Can you all see my pointer? Let me know if
Yeah, We can.
Great, great. Okay. So up to the point in time where this was the outer surface, the outer surface of the coral, the coral is growing radially upwards and outwards. But at this point in time, the coral experienced its first die down. And it died down to this point where my pointer is now. And so that was the highest level of survival at the time of that die down. But after that die down, the coral was able to grow radially upwards and outwards from below that highest level of survival. And we're only looking at one radius, but the same process happened on the other side of the coral. And this coral grew for a number of years until some later time when this was the outer perimeter of the coral, the outer surface of the coral, and it died down again to this highest level of survival. And you can see over here on the left, it died down to about the same elevation. And the process repeated until a third point in time when this was the outer surface of the coral. And it died down to this highest level of survival. And you can see contemporaneous die downs on corresponding parts of the coral. And then finally, it grew out for about another 6 years until 2004, the 26th of December 2004, when this coral was uplifted 1.25 meters and everything died. Now, if I trace the annual bands, you can see the annual bands in yellow here. And if you were to count the annual bands back, you would see that the die downs happened, the outer die down happened in December 2004. The penultimate die down was late 1997. Before that, late 1982. And before that, the initial die down was late 1961. So what do these die downs record? Well, the last die down records the 2004 uplift, of course. But the earlier die downs correspond to the 3 strongest positive Indian Ocean dipole events in this record. The Indian Ocean dipole, in case you're not familiar with it, it's the analog in the Indian Ocean for ENSO, for the El Nino, La Nina cycle. What you can see in this time series in the lower right is satellite altimetry. It's sea level anomalies for a site very close to where this coral was sampled from. And what you can see is that during the late 1997, early 1998 positive Indian Ocean dipole event, sea level was several centimeters lower than at any other point between the beginning of the altimetric record in 1992 and 2006, when I created this figure. And so, not surprisingly, this sea level was several centimeters lower at this point in time, and we have a die down of, actually it was a little bit more than several centimeters. It was about a little more than 12 centimeters. Now, the reason that sea level is lower at this location during Indian Ocean dipole and during positive Indian Ocean dipole events is because a positive Indian Ocean dipole is associated with a strengthening of the trade winds over the Indian Ocean. So normally at the equator, the trade winds blow from east to west. But when the trade winds strengthen, they're blowing even harder, even faster from east to west. And what that does is several things. First of all, it blows the surface water from east to west. And so that in and of itself supports a higher topographic gradient on the surface of the ocean. So off the eastern coast of Africa, sea level is higher than normal. And off the west coast of Sumatra, sea level is lower than normal. But also, a second effect, because the warmer surface waters are blown from east to west, there is the surface waters are replaced by colder water from a little bit deeper. And because the water is colder off the coast of Sumatra, the water is denser. And so just because of an isostatic effect, because of a buoyancy effect, the water is sitting lower off the coast of Sumatra simply because it's denser. So both of these effects lead to a lowering of sea level off the coast of Sumatra. So even though we don't have an altimeter record going back before 1992, we know that the three strongest positive Indian Ocean dipole events actually in all of the 20th century were in late 1961, late 1982, and late 1997. And sure enough, those are the 3 years where this coral recorded a die-down. So the take-home message here to start is that these die-downs are caused by this transient sea level lowering associated with the positive Indian Ocean dipole. So initially, I told you, I told you that there were different processes in different parts of the world that I don't know why that's here we go. So I mentioned that there are different processes in different parts of the world that cause these transient sea level lowerings. Off the coast of Sumatra, the main driver is the Indian Ocean dipole cycle. But if we go to the Philippines now, which is several hours flying time east from Indonesia, about on the order of 1,000 kilometers farther east, it turns out that the primary driver of sea level anomalies in the Philippines is the ENSO cycle, the El Nino Southern Oscillation. And so here, again, the trade winds at the equator normally blow from east to west, but during El Nino events, the trade winds either weaken or reverse. And so normally water is being piled up in the Philippines because of just these normal trade winds, but when the trade winds weaken or reverse, water sloshes back from the Western Pacific towards the Central and Eastern Pacific, and that results in sea level lowering around the Philippines. And also, just like in the Indian Ocean, the water temperature drops because you have less of this surface water being blown from east to west. And so that leads to denser water and lower water. And again, the trade winds, the change in the trade winds and the colder, denser water around the Philippines, both of these contribute to lower sea level around the Philippines. And so we might expect to see die downs during El Nino events in the Philippines. And so what we're looking at here is a record of the strength of basically it's the an index of the El Nino. So it's positive for El Nino events, positive in red for El Nino events, and negative in blue for La Nina events, with the strongest El Ninos being the darkest reds. And if we now, this is work that my former PhD student just published, but if we look at the timing of die downs at a site in Luzon, in Western Luzon, we can see that most of the die downs, and in fact, all of the bigger die downs, occur during the strongest El Nino events. And so we have, there are some more moderate die downs that occur in other years, but there's a very good correlation between strong and super El Ninos and large die downs at this site. So as we anticipated, but this is a very good demonstration of it, corals in the Philippines are recording die downs related to El Ninos. And that is what's responsible for giving the corals their form. But in addition to this high frequency sea level oscillation related to the Indian Ocean dipole or the El Nino Southern Oscillation, corals are recording other signals. So I'm going to ask you, if you want to turn on your microphones, what else do you think coral microatolls might record? Any ideas?
Come on, students, don't be shy. Or it will be an indication that you are sleeping.
Well, I'll give you a
sleeping?
hint here. I'll give you a hint here. So, or I'll ask a slightly different question, which is designed to give you a hint. So we're looking, this photo is, it's actually one of my favorite photos, and it's a site not too far from the site where I showed you this coral over here. So the processes are similar. So this is a site off the west coast of Sumatra, above a subduction zone. And so some of the same processes are happening at this site. So you're a marine geoscience department. What do you see in this photo? And I'll give you, what I'll say is, there are a number of observations you can make about this location that would be highly unexpected along a tectonically stable coastline. So if anyone wants to tell me what they see in this photo, you can chime in and just say one thing you see to get started.
Nobody is going
Uplift,
to
maybe?
I think
Okay.
I think the faculty is going to hop in here. Is there a student in there that wants to do it?
I said uplift, but maybe I'm mistaken.
Okay, so first of all, the easiest answer that probably no one's saying because it's too obvious, there's a coral microatoll here, right? And you're absolutely right. This coral microatoll is sitting out of the water, so it has been uplifted. So that's a great start. What else do we see in this photo?
Aaron, can I ask a question though? Are you talking about a microatoll that's in Sumatra?
This is a Sumatra. This is a microatoll that's in Sumatra.
Because I mean, earlier you said that it is tectonic, though. I mean, you're.
Oh, yes, right. So there are things that we observe here that are unique to tectonically active coastlines. So we do see them in this photo because of the tectonic activity in this photo, but we wouldn't see those same things. And I'm trying not to give away the answers here, so I'm speaking a little cryptically. We wouldn't see those same things in a tectonically stable coastline. So as an example, a coral, a recently living coral sitting 30 centimeters out of the water and dead, we would not expect to see that on a tectonically stable coastline. So I'll give you some, I'll answer the second question and then we can go back to the first question. So some other things that we see here. In the background, there are mangrove snags. So these are dead mangroves. We might consider these a ghost forest because these mangroves are dead. But we see living mangroves. Clearly, this is a much younger mangrove. These dead snags grew for a long period of time, and this young mangrove here is very young, maybe only a few years old. And it's at the exact same elevation as these dead mangrove snags. The dead mangrove snags and the living mangrove are all at the same elevation as this coral microatoll. Now, you might not be experts in tropical coastal processes, but I'll tell you that mangroves don't grow at the same elevation as corals. Even though mangroves can grow, can survive for part of the time being submerged, and it depends on the species and genus, they generally need to be exposed more than half of the time. So they're generally from around mid-tide and above. And the corals, even though they can survive a little bit out of the water, they're really near the base of the intertidal zone and lower. So you would not expect to see on a stable coastline mangroves and corals coexisting at the same elevation. So can you come up with an explanation? Can you propose a history for what might cause all three of these to coexist at the same, maybe not at the same time? There are dead mangroves, living mangroves, and dead corals all at the same elevation in this scene. So remember that the concentric rings on this coral are telling us that the coral was growing up to sea level throughout its lifetime. But I hope you can see it. The rings in the center are lower than the outer perimeter of this coral. So in addition to the high frequency changes related to the Indian Ocean dipole at this location, this coral is recording gradual relative sea level rise over its lifetime. The gradual relative sea level rise meant that every decade, this coral had a little bit more space to grow, a little bit more room to grow up. So the coral was really happy. But at the same time, that gradual rise in sea level was drowning these mangroves back here. And eventually those mangroves died because they were drowned, because they were submerged too long, too much of the time, too high a proportion of the time to survive. But then this was actually not during the 2004 earthquake. This was another earthquake 3 months later in 2005, a magnitude 8.6 earthquake. this site was uplifted by about 0.5 meter. The uplift killed this coral microatoll, but all of a sudden, it created space where new mangroves could take root and start growing at the same elevation as the older mangroves. So this scene, and in particular this coral, records both gradual relative sea level rise as it grew. It records the high frequency changes related to the Indian Ocean dipole. And finally, it was killed by coseismic uplift. So this coral records all of that. So let's go back. Let's spend some time now on this island. This is Simeulue Island, which is at the boundary of the two earthquakes I was just telling you, the two rupture patches I was just telling you about. So the magnitude 9.1 earthquake in 2004 resulted from rupture along this 1,600 kilometer patch to the north of the island. And 3 months later, about a 450 kilometer patch ruptured in a magnitude 8.6 earthquake. And this island, Simeulue Island, really straddles the boundary between those two rupture patches. So I'm going to spend a little bit of time now talking about some observations on that island. So first of all, going back to the slab that I showed you earlier, the X-ray of the slab, before I was focused on these changes related to the Indian Ocean dipole, but we can see if we plot a trend through the highest points, we can estimate a gradual rate of change. And this is an interseismic submergence rate of about 1 centimeter or 10 millimeters per year. Now that is the combination of anthropogenic sea level rise as well as interseismic subsidence. We can do the same thing with fossil coral microatolls. And so this was a coral that was at a nearby site. We dated it with uranium thorium. So we know how old it is, but the coral records gradual relative sea level rise over its lifetime, followed by about 0.5 meter of a die down that we interpret is related to coseismic uplift in an earthquake around the year 1394. And at the same site as this coral, we actually found multiple generations of corals. And we were able to reconstruct a time series for about 140 years, 130 years of sea level changes from these different generations of corals. And just to illustrate, so what this plot is showing is the highest level of growth and the highest level of survival from a number of different corals. It turns out, we didn't know this until we did the careful work and we dated the corals, but several of the corals very close to the coastline had actually slumped, presumably from shaking during the earthquake, from one or more earthquakes. But corals farther inland were plotting at more consistent elevations. And we see one generation, we see an older generation of corals here. And just to show you some photos of those corals, every coral in this generation is characterized by a lower center and a double outer ring, 2 rings on the outside that are all about the same elevation. And all of them are showing a relative sea level rise over their lifetime of about 3.5 to 4 millimeters per year. And they all date to the 14th century, from about 1320 to about 1394. Then at the same site, we see another generation of corals that have a very different morphology, and they're slightly lower. They have a lower interior, a high middle ring, and then a lower exterior. And all of those corals, again, there was one coral near the edge that slumped, but all of them have the same morphology, and they're giving us the same age, and they fill up this later part of the curve. And so from these different generations of corals, we're able to put together this sea level curve. We have relative sea level rise, which we infer is from gradual interseismic subsidence, a sudden die down of about 0.5 meter related to coseismic uplift. And then we have some post-seismic, what we interpret to be a post-seismic subsidence, and then interseismic subsidence, another small uplift event from another earthquake, more interseismic subsidence that leads to gradual relative sea level rise, and then finally, all the corals at the site are killed, presumably due to uplift, although because everything was killed, we have to speculate a little bit about what the cause is. So from this, we infer 3 earthquakes. The first in 1394, the next, a smaller uplift event around 1430, and then we infer a third uplift event around 1450. And one more thing I should point out on this figure, in all of these corals, they start growing way below low tide. And so what the initial part of each coral record is recording is not something related to sea level, but they're simply recording the coral growing up to sea level. So you shouldn't pay too much attention to the fact that the start of each coral record, and each coral record is indicated by a unique color, the start of each record shows this steep rise, but that's just the coral growing up. But then once the first die down occurs, which is indicated by the first circle on each coral record, then the coral record reverts to a fairly consistent rate of relative sea level rise. And if we look at different corals from different generations at a given site, we see this is a different site now than the one I was just showing you, but you can see one of the things that we really learned from this study, from these corals, is that at different seismic cycles, different portions of a seismic cycle, and then different seismic cycles themselves, between one earthquake or leading up to one earthquake compared to leading up to a different earthquake, we have very different rates of interseismic subsidence. And so this suggests that for those of you who are interested in tectonic studies, that the coupling ratio, or the rate that strain is accumulating on the fault, actually changes over the seismic cycle and from one cycle to the next. And this challenges a long-held assumption in earthquake studies and in earthquake hazard studies that strain accumulation is fairly constant. And we see evidence here that it actually varies a lot more than was previously appreciated. But if we look now at, so here we are looking at the entire island of Simelu, and the island from the northwest to the southeast is about 100 kilometers long for scale. And each circle here represents a unique site, a different site where we have information on the uplift in 2004 or 2005. Remember, this island straddled the boundary between the 2004 and 2005 ruptures. And what we see in warm colors are sites that uplifted a significant amount. And in the cold colors, we see sites where there was very little change. And so what we see here is that in 2004, in the magnitude 9.1 2004 earthquake, sites on the northwestern part of the island were uplifted more than half a meter. And sites in the southeastern part of the island had very little change. In contrast, in 2005, 3 months later, sites in the northwestern part of the island had very little change, but sites in the southeast were uplifted more than half a meter. Now, and so this gave us the idea that we wanted to know, well, why did the 2004 rupture stop where it did? Why didn't it just propagate all the way through the island and continue on to what became the 2005 patch 3 months later? For whatever reason, this region here between the two patches acted as a barrier to rupture in the 2004 and 2005 earthquakes. And so we wanted to know, what has this patch, is there something special about this region, this part of the island, this part of the megathrust? Has it behaved this way in the past, or was this kind of just a random one-off fluke that we shouldn't expect will behave the same way in the future? And so here again, this is the same image I just showed you, the same two maps from 2004 and 2005. And if we now go back to earlier earthquakes, earlier ruptures over the past 700 years, what we see is that repeatedly over many earthquake cycles, earthquakes that uplift a majority of this island can be categorized largely into two types of earthquakes. Earthquakes that uplift the northwestern part of the island, such as 2004, 1450, or 1394, and earthquakes, ruptures that uplift the southeastern part of the island, such as 1422, 1861, and 2005. But we have no rupture in the entire record that simultaneously involved uplift of both halves of the island. So the answer to the question is that this, whatever was the barrier to the rupture in 2004 and 2005, has been a persistent barrier to rupture through every major earthquake, every major rupture in the past. I realize I'm running late here, so I'm going to speed through the next few slides here. We also saw some smaller, moderate, some more moderate magnitude 7.3 and 7.4 ruptures that affected only the central part of the island in 2002, and another one in 2008. And we, in addition to this, and this is work from Luja, who was a postdoc back then, she's now faculty, and Paul Morgan and Louisa Tseng, who were students at the time. And what they looked at, not only the uplifts in the big 2004 and 2005 earthquakes, they also looked at the uplifts in the more moderate 2002 and 2008 earthquakes. And they also looked at the interseismic strain accumulation rates from corals at many different sites on this island. And they mapped out the coupling ratio, the coupling pattern over the 20th century leading up to the 2004 and 2000 earthquakes. And what they showed is that there are the 2004 and 2005 ruptures correspond to strongly coupled patches. There is a third smaller coupled patch in the central part of the island, and these three coupled patches are separated by two separate zones that are much more weakly coupled. The coupling is much less, and so there's a strong correlation between coupling and where there's slip and the boundaries of these different ruptures. Frederick Tillman has also showed that if you look at microseismicity, there are also some changes that are co-located with the changes we observe. And if we look in the oceanic plate in the Indian Ocean, that's part of the downgoing slab that projects into this downgoing slab, we see there's a fracture zone as well as a topographic, a nearly north-south oriented, it's about north-5 east oriented topographic ridge that projects right into this barrier region in Simeulue Island. And so we see there are changes in coupling, there's relief in the downgoing slab, and all of this seems to control rupture segmentation over many earthquake cycles. So that is just some of the observations. These are the key observations that we were able to make in Sumatra from the coral microatolls that we really could only make because of the resolution that these corals give us. I'm going to speed through some newer results from the Philippines, but what I want to say is we've done similar work now in the Philippines. The sites in Sumatra and the sites in the Philippines are similar distances from the megathrust. All of our sites are about 120 kilometers from the megathrust. But one big difference in the Philippines and Sumatra is the dip angle of the slab. The Sunda megathrust is dipping fairly gently under Sumatra, but the Manila Trench subduction zone is dipping much more steeply under the Philippines, under Luzon. And what we're looking at here are these lines are isobaths. They're structural contours on the top of the slab, and so where they're closer together, the slab is dipping more steeply, and then the stars are representative of our coral microatoll sites. The key difference here is that in Sumatra, in the left panel, all of our sites are between 20 and 30 kilometers, are over places on the megathrust that are between 20 and 30 kilometers down, whereas in the Philippines, our sites are generally over places where the megathrust is 40 to 50 kilometers deep. And this has profound effects on where the locked patch of these faults, where the locked patches of these faults are relative to our sites. So if we look at our site in the Philippines, here's the coral again from the title slide. And what we see here is there are a few die downs at the beginning of the record, and then the coral is suddenly able to grow up nearly 40 centimeters over about 20 years before the next die down. And this is an indication that the coral was growing up to its highest level of survival, and then all of a sudden, its highest level of survival rose by about 40 centimeters. And so we interpret that this is a sudden subsidence event. The coral was suddenly brought into deeper water. And so this coral, unlike the corals in Sumatra, which experienced coseismic uplift, this coral seems to experience coseismic subsidence. I'll skip ahead. We have multiple generations of fossil microatolls at this site. There's also a generation of living microatolls at this site. And when we put this record together, this is work that Gina, my PhD student, did, we see a record of the coral started growing. It had a couple of die downs. It then experienced coseismic subsidence. It then continued to experience interseismic subsidence. Then there's a long gap in the record. So this figure kind of hides about 800 years of a gap, a little more than 800 years. But then the record picks up. We see another coral with a subsidence event, more interseismic subsidence, and then finally the living coral growing up to present sea level. We have another 2 sites farther north that are a little bit closer to the trench. They experience, we see the corals rising rapidly. This is back in the mid-Holocene, so we think this is sea level was still rising rapidly due to melting of the Laurentide and Greenland and Antarctic ice sheets. But then we see abrupt sea level fall at 2 sites, which we think represent a coseismic uplift event, and then before relative sea level rise resumes. And so the style of deformation at these different sites varies depending on each site's relationship to the active faults and the locked parts of each of the active faults. But the corals really allow us to resolve a lot of details about the uplift and subsidence histories, both interseismic and coseismic, at all of these sites. And so to wrap up, and I apologize for going over here, the coral microatolls really provide insight in a number of ways into the past. They help us constrain coseismic and interseismic deformation. We can learn about rupture barriers, we can learn about coupling, and we can see deformation over the entire seismic cycle over multiple seismic cycles. And finally, just to, as I promised, I would generalize at the very end of this talk to say what the corals can tell us in tectonically stable places, or just about relative sea level in general. And if we compare the corals to conventional techniques for reconstructing relative sea level, coral microatolls offer important advantages. Most sea level proxies, and for any of you who do sea level studies, you probably know what I am referring to. Most sea level proxies, and so these could be in the tropics. In addition to corals, these could be mangroves, these could be oysters. In more temperate mid-latitudes, these could be salt marsh grasses. These could be, and often microfossils, so diatoms or forams will be used to reconstruct changes in sea level. But most of these sea level proxies provide a set of independent sea level index points. So you find one data point in a sediment core, or one oyster, or one barnacle, and that or even one archaeological site, for those who use, and I know in Israel, there's a lot of archaeology that provide useful constraints on sea level. But these give us isolated points. And so if you have one sea level index point that you derive from one feature at one elevation and you date it and you have a point in time associated with that elevation, and then you have another sea level index point at another time and another elevation, each of those points has often has significant chronological uncertainty. Maybe in the case of archaeological sites, you have much more precise chronology, but a lot of these sea level index points have very large uncertainties chronologically, if not also vertically. And so if you want to estimate the rate of sea level change between those 2 points, you end up with high uncertainties in the rates, because the uncertainties in the age and elevation of each index point propagates into the uncertainties in the rates. In contrast, the microatolls provide continuous records of relative sea level, and over the lifetime of a coral, which might be anywhere from a few decades to a few centuries, we can count the annual bands, and we have essentially zero relative age uncertainty over the lifetime of a coral. So this gives us much more precise estimates of rates of sea level change. Many sea level proxies are developed from sediment cores, but the sediments accumulate only where there's sufficient accommodation space. So that's generally only where there's rising sea level. And so we don't get good sedimentary records where sea level is stable or falling, because there's no accommodation space for new sediments to accumulate. And those sediments are prone to compaction, which creates a potential bias in the sea level reconstructions. In contrast, coral microatolls commonly grow on reef rock substrate that's not prone to compaction, and they can thrive in conditions of rising, stable, or even slowly falling sea levels. So they give us data sets, and reliable data sets, in many places where we can't rely on sediments. And finally, many sea level proxies have vertical uncertainties of 0.5 meter or more, whereas the microatolls commonly have vertical uncertainties of about plus or minus 20 centimeters of 2 sigma or better. So these coral microatolls are precise, and where we can find them, they provide some of the best archives of Holocene sea level, Holocene relative sea level anywhere in the world. So with that, I'll end there.
Thank you very much, Aaron. It was indeed very comprehensive talk, and very enlightening for us, and that we are not used to this kind of landscape. I open the questions for students, and don't be shy, or anybody else who wants to ask. Somebody?
Hi, thank you for the lecture. It was really interesting. I wanted to ask, maybe I missed it, but can you tell us about the world distribution of microatolls?
Sure, yeah. So it is generally, they are generally limited to warm tropical waters. So I mean, we tend to find microatolls wherever corals grow. So corals grow in the coral triangle in Southeast Asia, in the Indies, and we find microatolls at sites throughout the coral region in the Indies. There have been coral microatolls found in the Caribbean, in the central Indian Ocean. They tend not to grow on even in tropical regions in the colder waters, the colder western boundary or eastern boundary currents, the currents at the eastern ends of the eastern edges of the different ocean basins. So the water's too cold off the west coast of North and South America. The water's too cold off the west coast of Africa. So we tend not to find corals there. But in general, where we see corals, we've found microatolls.
Thank you.
More questions? Well, I think that we are like really beyond time.
Sure. Yeah.
So-
Sorry for going over.
No problem. So if I have some questions actually, but I will ask you, it will be a long question. So I will ask you in an
Sure.
email, okay?
Sure. I look forward to that.
I guess that you need to go to get overcome the jet lag.
Yeah.
So thank you everybody for attending, and thank you again, Aaron, for this beautiful talk. I really hope to be there in this kind of landscape.
Yeah. Come and visit us in Singapore.
Great.
Thank you.
Thank
Very
you very
good.
much.
Thank you.
And have a good day over there. Thank you.
You
Bye bye.
too.
Thank you.
Bye-bye.